Yeah, we're ready.
All right, I'll just give you a very short introduction. Hi, everyone. Very nice to have Gregory Chaplain from the University of Exeter to give our seminar today. Greg helped us out with winter school at the beginning of the programme, and he's now back for this week and next week for our workshop. That's all I need to say, really. Greg, it's over to you. Have you give more of an introduction if you like?
Great, thank you, Luke. And well, thanks for having me back after the winter school. It's been a really nice week so far. So yeah, I'm from the University of Exeter, based in the Centre for Metamaterial Research and Innovation. So the talk will be loosely about metamaterials, and so I've entitled it Beyond-Nearest-Neighbour Metamaterials, and I've added this little subheading of new trends because this seems to be quite a hot, in vogue topic now, and so hopefully I'll be able to convince you that it is, and there's definitely a flurry of research in this field, but we might actually ask the question that it's not that surprising in some of the results. So although it's a new trend, it's actually quite old, so that's what I'll endeavour to show. I'll just give a very brief overview if my laptop catches up. So I'm going to talk about two systems, an elastic and acoustic, Beyond-Nearest-Neighbour Metamaterials. So I want to start just by a very brief recap of bound surface waves, start off in electromagnetism and talk a little bit about where the metamaterial piece of that comes from, even though I'm sure it'll be very familiar to everyone. Then I'm going to introduce this idea of beyond-nearest-neighbour or non-local interactions. And the only maths that will be in this talk, I think there's maybe two equations, and it's just masses and springs. So please bear with me as the physicist in the room. Then I'll give two examples and some experiments that we've done on the structures that I'll highlight below, and then hopefully round off with some applications which might be familiar to some of you if any of you saw the talk in the winter school. So a very brief overview of bound surface modes in electromagnetism. So it's been well known for some time that if we have an interface between a conductor and an insulator, there is a mode that propagates along the interface and exponentially decays into both half spaces. And this happens naturally when we have a change in sign of the real part of permittivity. And so conventionally for metals, this occurs at visible wavelengths. And so the coupling of the electric field and the motion of the oscillations of the electrons in the conductor, and the combination of that is called a surface plasmon. And so there's this asymptotic frequency that your dispersion relation tends to. But at lower frequencies down here in the dispersion, we basically have no interesting effects. The modes follow the light line, and so this is typically in the microwave region where the metal behaves like a perfect electric conductor. And if you look at a sort of schematic of what's happening with the fields, it's very small penetration into the metal, and into the dielectric, the wavelength extends hundreds, or the decay length is hundreds of the wavelength. And so actually down here, nothing really interesting is happening, and it just looks like a free surface current. And so a question that arose is, how can we tune this asymptotic frequency? And that's sort of where one of John Pendry's seminal papers came in. And this is where the meta piece of this arises from, by adding some sub-wavelength structuring, some periodic array of holes here filled with the dielectric, and they could actually tune where this asymptotic frequency behaved. And so you get a very similar surface wave-like plasmon, and they called it a spoof plasmon. And then in the next issue of Science, this was experimentally verified by some of the researchers at the University of Exeter. And so here's some schematics from their modelling where you see the electric field in the pointing vector. It really has the character of a surface wave that's localized to the surface and decays exponentially into the metal and into the dielectric. So that's just a whistle-stop tour of the type of waves that I'm going to initially talk about manipulating, but I don't really do any electromagnetism. I work in acoustics and elasticity primarily, and so there is a very simple acoustic analog to this with a rigid grating of grooves in some sound-hard material. So just a note here that the unstructured analog doesn't hold. We don't have a surface acouston, that doesn't exist. But we can see, and in the next slide I'll show, the dispersion relations that are very analogous to this spoof surface plasmon mode, where we have some resonance which is dictated by the geometry of our cavity, basically. And so that's what we have here. We have these acoustic modes that are supported by such an array in two regimes, what we call the radiative and non-radiative regime, that's delineated by the sound line. And so there's these two flavors of modes which are supported by the geometry. And so in the radiative regime, these are modes that can couple to planar waves and originate through thermal visco losses effect in your cavities. And so on this dispersion diagram here, I'm plotting the in-plane wave vector. So this is the wave vector that's parallel to our surface. And so that's actually related to some incident wave vector K0. So we can think as slices up, this being at different angles of incidence. And this is indeed how most measurements are done on these types of surfaces, that you will fire a wave in and look at the reflectivity profile. This is a snapshot from the experimental confirmation of the spoof plasmon mode. So we're not thinking about gigahertz acoustic frequencies, don't worry about that. And so they live up here, and it has some resonance which is dictated by the geometry of our cavity, the depth and the width, etc. And then also we get modes that are bound below the sound line. So critically, these have momenta which is greater than the free space wavelength. And so this is localized to the surface. So this is what I would call an acoustic surface wave, because it's an actual acoustic pressure fluctuation. It's not a surface acoustic wave, which would be more like a Rayleigh wave. There's sort of an important distinction there. And that has an asymptotic frequency, which is very, very analogous to the spoof plasmon case. And so you can stick those two things together, and basically there's some fundamental resonance which dictates whereabout these guys occur, and it's down to the geometry that we've endowed our surface with. And so these are the types of waves that I'll hopefully be able to make a little bit more interesting in their dispersion relations. And so these are just some examples of some of the work that's been done in Exeter over the past few years. The next few slides were provided to me by Dr. Tim Starkey. So if there's any questions or comments about them, I'll just direct you to him. But basically, what gives us this surface wave is the near field diffractive coupling from the holes. And so provided that these holes are close enough, we'll get these types of surface waves on any geometry of them. And so the canonical example that was investigated some time ago now was just an array of holes that's drilled into some perspex plate. And at the frequencies in air that we were looking at, or that they were looking at, this was before I arrived in Exeter, you can approximate this as a sound hard surface, so that's very nice. And what they do is they put a source in one of the holes and excite one of these surface waves, and then take a scan in space and do the spatial temporal Fourier transform and recover the dispersion relation, which you see here. So we have the sound line here, which delineates the radiative and non-radiative components. And we have this nice asymptotic spoof plasmon acoustic-like mode here. And at different frequencies, we can see the sort of character of the mode. When we're beneath the cutoff, unsurprisingly, we have a mode which propagates along the waveguide. And as we get closer and closer to the cutoff, less and less energy propagates. And then when we're above it, we're now in, we are supporting no propagating wave, and we just have an evanescently decaying solution along the waveguide. There's a trick of the eye here. This looks sort of funky because it looks like the wave's going in the opposite direction, but that's just an interference effect from the source being placed near one end of the waveguide. So this is experimental data, yeah, exactly. So they yes.
Coming back my mind, I'm thinking like photoelectricity.
Yes.
Rain.
Exactly. Yeah, so I've not looked at that, but that's exactly right. But unlike in the acoustic case, that will exist without any periodic structuring, because you have sort of Rayleigh waves, or depending on the thickness of your plate, say you'll have Lamb waves and all sorts of things that exist without the structuring. The thing that makes this meta is that we've added some periodic holes to this essentially. But yes, you're exactly right. There are elastic analogs as well.
Can I ask one bit?
Yes.
So you have it. Can you explain again what's happening with the top wall?
This one here.
Yeah. You said about the back.
So above here, we don't expect any propagating solution, right? It's just a decaying one. And so it looks like it's going back. So it's essentially some beating phenomena, because the source is placed very close to one end here. So you get reflections from that end.
So is So if you look at the bottom of it, I mean, it's less obvious, but I think the ones underneath also have some propagation, or is that just me?
I think this is probably a trick of the eye. So what is actually happening in these pictures? We're being a little bit sneaky. This isn't time domain data. So they take a scan in time and space, do the Fourier transform, and then you can have a snapshot of the field at one frequency, and then they've just timed this by e to the I5. So we're just cycling through the.
Oh, okay.
Yeah. So and we'll actually see something very similar to that later in the talk. Another sort of trick of the eye. Here,
Yeah.
yes. So this horizontal line is when we excite at this frequency, which is this bottom plot here, and then the second horizontal line, we're still on the dispersion branch, so we still excite a propagating wave here. Obviously, there's dissipation in the system, so we don't excite forever, and there is a decay associated with the propagating wave. Yes, exactly. Yeah, exactly. Yeah, they're purely just to show what frequencies lie where on the dispersion. So a question is, how else might you tailor the dispersion? Because at the moment it's not particularly exciting. We've just got an array of holes, and that gives us this asymptotic frequency, which is very nice. As I said, this exists because of this near field diffractive coupling. So this is like the nearest neighbor argument, that the diffractive fields from this hole sort of spill out into the next one, and so on and so forth, but they don't talk to any neighbors further away. So provided that they are sufficiently well coupled, whatever this means, and that they are close enough, you can get these types of waves on any arrays. And so they then did some other experiments where we put this thing in a ring. So you have some notion of an angular wave vector here. This is a scan now in 2D, and they play the same games that they did before. Or you can make it a 2D periodic phononic type crystal, and you get very classical effects such as anisotropy. And so that's some experimental data that was done a few years ago now in Exeter. So on that point, if anybody has any nice acoustics experiments they would like us to do, I can happily volunteer my colleagues' time. So, because to them, I'm the mathematician in the group, but to the mathematicians, I'm the experimentalist, so I have this nice trade-off. So I'd like to return to this question, is how else might we tailor this surface mode dispersion by taking into account these beyond nearest neighbours? And that's the motivation behind this, is that there's been a recent flurry of interest over the past few years in these beyond nearest neighbours, or sometimes they're called non-local interactions in metamaterials. And that was largely because of this paper here by Martin Wegner's group, which is a very, very nice paper. And what I'm away to say might sound like I'm slagging it off, and I'm absolutely not. But there's this buzzword here, roton, which the community has really, really picked up on, and which is a good thing because a lot of people are now interested in these types of materials. But what I'll show is that actually roton might not be as obvious a term as they're claiming. But there's been several review and Physics World articles that have come out of this based on the very exotic structures that they theorize, design, and test, and it all works very, very beautifully. But one of the things that these roton-like dispersion relations have, and I'll show that in a slide's time, is that they excite backwards waves. And so backwards waves are when the direction of propagation and the direction of energy flow, the group velocity, are anti-parallel. And in this review, this Physics World piece, they said that backwards waves have only been observed in ultra-cold quantum systems. So immediately it sounds very, very sexy, very exciting. That's not strictly true, though, because backwards waves exist naturally in elastic materials and plates and pipes, and they've been known to electrical engineers for a long, long time. So the metamaterials community, we might have reinvented the wheel again, but that's, as I'll hopefully show, no bad thing. So what is roton and what constitutes roton-like? I had no idea what a roton was when I read the paper, so I had to go to Wikipedia and find out what it was, as all good scientists do. And so it turns out a roton is a quasi-particle in superhelium-4 and Bose-Einstein condensate. So immediately it doesn't seem very relevant to periodic acoustic metamaterials. But the sort of key point is that there's long-range interactions, some dipolar coupling or some spin-orbit coupling. And this is where the motivation for this beyond nearest neighbor phenomenon comes in. If you now look at the Wikipedia page for Roton, because the community is so excited by this, this paragraph has been added saying that Roton-like is now used to describe 3D metamaterials. So that's how much traction this has get. Admittedly, one of the authors of the paper probably added this, but that's their right, so fair enough. And so why you see this is because in these materials that I'll highlight in a few slides' time have a dispersion relation, which is now more interesting than the classical one I showed earlier, in that there is turning points within the first Brillouin zone. So they have maxima and minima. And it turns out that this has the same number of maxima and minima as a Roton in their dispersion relation. Although they are evidently quite distinct fields. This is quantum whatever. This is a periodic system. The turning points here are at very well-defined k-vectors, as I'll show. And but they have this nice maxima and minima. So that's why it's Roton-like. And so people are getting very excited about this. And so just to sort of show where this comes from, on the left-hand side, this is a Roton's dispersion, and they're using this to predict deflection angles of phonons, in some superfluid helium state, and it's all very complicated. But this Beyond-Nearest-Neighbour picture in metamaterials comes in a very simple mass spring model. So what I showed earlier with the near-field diffractive coupling from these sound-hard cavities, you could think of the air in the cavity as a mass and the diffractive coupling being like a spring. So we have a chain of masses and springs, and we would get a usual branches I showed earlier. If you then extend some interaction to a mass that's beyond the nearest neighbour, n number of unit cells along, then you introduce these turning points. And this is from the paper that Martin Wegner's group first wrote on this, and they look at what happens as you vary, in essence, the spring constant of your next nearest or next nearest neighbour. And you see, as you increase the strength of this, you get more and more Roton-like, such that if you make this very, very, very strong, then it's almost like you have changed the size of your unit cell, and the perturbation is now from the weak spring. Of course, we don't actually third the Brillouin zone because the irreducible Brillouin zone, as we know, is determined by the geometry. So that was one of the challenges actually in incorporating this into metamaterials, is how do you tune this? How can you make the coupling strong? And actually, as I'll show in a few slides' time, in mechanical systems, it's very, very easy to make it strong, because we're going to physically bolt some things together. And so just to sort of highlight this a little bit more and sort of why this is sort of the new vogue, even though it has been around for a while, I thought we could, so this is the dispersion relation slide that they show. So this is the classical dispersion relation, which I'm going to do in the next slide. And then there's this extra term, which depends on the order of interaction. So I thought we could all return to my maths for this talk and our favorite. Yes?
What's the length of the additional springs? Is that just 3 times 8?
Yes, exactly. It's just 3 times. So in this 1D picture, they all cross. And so actually, in real life, as we'll show, we have to go to the third dimension because we have to make these things not touch. Yeah. And so let's go to our favorite textbook, Brillouin's book himself. And on page 4, he shows us our very classical mass spring model. He models atoms with some interaction between them. We know exactly how to solve this if we're considering masses and springs, and let's say these are the displacements of our springs and some spring constant gamma. We write a difference equation, we use Bloch's theorem, we get the dispersion relation, and out pops our dispersion diagram. And altogether, not that surprising, we have 1 degree of freedom, so we have 1 band that we can represent in our irreducible zone. And so you think, oh, well, the extension from this to next nearest, however many nearest you want, we just add more terms in here. So you think, well, did Brillouin miss a trick doing this? No. If you just skip forward to page 33 in the version that I have, he has this discussion on the distance of interaction and writes explicitly, if you extend this to the elf neighbor, then this is what your dispersion relation looks like. And on the next page, he again explicitly states that the polynomial, the frequency or our dispersion relation will be expressed as a polynomial of degree L. So we're expecting for the elf nearest neighbor to have L minus 1 extrema within the first Brillouin zone. And then he shows a dispersion curve, which arguably is more exotic than a Roton-like one, just by playing with interactions strength. And so that was then exactly showed in this sort of review article on this hot topic. So in blue here, this is when they're the next. So this is our roton-like. They go up to 4, and you get 3 extrema in the Brillouin zone. This one in A doesn't seem that exciting, and maybe because it doesn't have some quantum analog, but this has been known for a long, long time, particularly in the metasurfaces community in electromagnetism, where you have competing powers of competing channels of power flow along different circuits, and so that's been well known for some time, but it's not been called something sexy. But a note on that is that these long-range interactions are very, very complex in complicated periodic things. If you've ever looked at the atomic band structure for anything where you account for spin-orbit coupling, spin-spin coupling, and you model this through tight binding models, KP perturbation, density functional theory, all sorts of things. So crazy dispersion relations aren't that unusual, but the key thing that we want to do in metamaterials is control this coupling strength, and that's hopefully something that I will be able to show you in the next slide. So let's go to the next nearest neighbour first of all, and we're going to look at some acoustic surface waves, so manipulating the types of waves that I showed that boring dispersion at the start at the top. And so let's just remind ourselves, we have some conventional canonical array of holes. This is my periodic unit cell, some sound hard thing, and I drill some holes in it and make it periodic. We get this dispersion relation here, and I've coloured in the plots to show that the direction of the group velocity is the same as the phase velocity, it's positive. And then if we add some complicated internal structure that connects not just, so the near field coupling is dictated by the mouth of the cavities, that's the near field diffraction, but then we add some additional tubes. I'll show a zoom in of this so you can see it, such that there's some internal structure that mediates this next nearest neighbour interaction. And you see we now have 2 families of modes. We have 2 because of some symmetries in this structure that are degenerate, and then I've coloured the acoustic intensity along the device. Basically, the group velocity, it's now positive and negative, which matches the gradient of our dispersion relation, which isn't altogether that unsurprising. And so this is what the structure actually looks like, and how we fabricated it. We 3D printed this with 2 different materials, one of which is water solvent. So we 3D printed this complicated internal structure. So the holes here, that's the tops of these guys, and that's where our nearest neighbour interaction comes from. And then we have these tubes or straws that connect one hole here to 2 cells along. And then we wash this guy out. And so what we have is something that looks like a boring old array of holes, as I showed at the start, but has some internal structure that mediates this next nearest neighbour coupling. And so what do the wave fields actually do in this structure, and what do they look like? And so this is just from some finite element modelling. And the purpose of this slide is just to sort of convince you that we've now introduced another channel in which the power can flow. And it's this competition between the power flow channels that drives the extrema within the dispersion relation. And so the colours here, this shows basically the direction of energy propagation. And actually, yeah, so the red and blue here is that, the red and blue here is just maximum and minimum pressure. And so at the mouths of the cavity, top and bottom, when we're on one where we think, okay, the group velocity is collinear with the phase velocity, you can see that it looks like both power flow channels are in phase. If we go right to the top of the turning point, we hit 0 group velocity, we have no net power flow, we have a standing wave, but this isn't due to the Bragg condition because it's slap bang in the middle of our Brillouin zone, and then so what we have is a standing wave that originates inside the tubes. And then if we look at this negative sloping region, you can your eye might trick you here, and you can see it that the top and the bottom surface, the wave looks like it's going in one direction, and in the middle surface, it looks like it's coming in the opposite direction. So it's kind of a trick of the eye, but actually when we measure this is true negative dispersion. And so that's something that we then went to test. Yes.
So here you have computed dispersion.
Yes.
And represented associated with
exactly. So these are just eigen solutions tiled and then hit periodic extension.
How?
So this was all through finite element modeling using console. Yeah. So you set up your unit cell and you put Fouquet block periodic boundaries. You then find each of the eigensolutions, and then you get the eigenmodes associated with that. So above here, yeah, exactly. We put a region of air and surround it by a perfectly matched layer, so it simulates. Yeah. It's a bit of a trick. Please, yeah.
Here, the X point decided by what length?
This length here. It's just exactly the same. So on the previous slide,
Between two poles.
yes, between two holes. So they have exactly the same unit cell spacing, and so actually
Given by the distance between two poles.
exactly, yeah. We don't change the size of the unit cell.
Numerically, when you are computing your problem and when you are making the period problem, what is the period you choose numerically?
Numerically, it's just this. It's the same. Or do you mean the actual value?
No, but if you plot your system,
This one.
what is the period that you choose?
So these are from the unit cell.
Yeah, what is the unit cell in that case?
It's what's shown in here. So actually, it's maybe not so clear on this one, but although the tubes extend out, you can just chop them off. So it looks like this is not connected to anything, this tube, but when you tile it periodically, it connects to the one from the cell.
The next is not the periodicity, the total periodicity that we see here.
No, so you mean this length here?
I know, if we just naively take the periodicity of what we see here, we have to take 3 times the distance between the hole, something like that.
No, you don't. This is the true unit cell here, and it's exactly matched here. So the unit cell you get, you just chop off here, and so this hole, you make the system periodic, and so in the unit cell, it looks like there's a tube that's not connected to anything. It's just sort of floating there. And numerically, that's fine, because we just say, well, this point here will, if I tile it, then we'll connect to this point here. So it is, we haven't changed the unit cell size at all.
But in this point, the period is not even the period between the holes at the top. It was I don't know what.
Well, okay, so I see. So this separation here, yeah. So that's what it is, because I just move it half a unit cell along, and so the separation of those holes is the same as the separation from midpoint in between the holes.
Yeah, but the structure see below it doesn't have that.
Yes, it does. Yes, this. It's funny. I haven't shown the unit cell particularly clearly in this one. I'll grant that. In the next one, if you bear with me when we get the Alastair one, I do show it very clearly, and I cut it in thirds. So bring me back to that point if it's still not clear, but hopefully there I'll get to it. So I have shown it very clearly, actually. So these are the unit cell. This is the unit cell. So the distance from this corner to this corner is the same as the distance from the center of the hole to the center of the hole in the next one. And so the Floquet block conditions are on this side and the other side. So you see this tube in the middle here looks like it's not connected to anything. But when I make it periodic, the entry to this tube here connects to the exit of the tube on the other side. Is that clear? It might be clearer, even clearer in the next one, hopefully. But the point in this slide, so this is exactly what I showed before. I've just gone to pink and green for the energy flow, and I show some of the eigenmodes here as these are degenerate because the system is symmetric. I can rotate it, I can flip it, whatever. But then if I add some covering to one side of it, I've then broken a symmetry, and so I then mix the modes and I lift this degeneracy, so we can open up band gaps and play all the usual types of games that we like to play with metamaterials. And so that's exactly what we then went to confirm experimentally. We have some scanning stage in Exeter, and we have two loudspeakers that we put near the holes of our structure. And the point of having two is that we can excite them in phase or out of phase, which can preferentially excite the symmetric or anti-symmetric modes. And then we can cover one side of our sample, and then we see that the dispersion relations match very, very nicely from our predicted eigenfrequency models in the acoustic case. Does that make sense? Cool. So So in this case here, it's because we have open cavities top and bottom, and the system is symmetric. So if you look at the eigen solutions here, they can be odd or even around the plane that divides the thing. And so it just so happens that they occur around about the same frequency. So they are accidental.
You're only considering that's the end.
Yes.
So, should be is there any thought about the process we have this like not in line?
We haven't actually. We normally just stick them at the end because then we're going to couple, which is so these. I mean, these are all subsonic, so we're not going to excite these with a plane wave. So we need to put our approximation of point sources very close to the cavity, and it's the diffracted fields that leak through this and couple. So we've not played really around with moving the source. I think in this sense we would just get less signal from our structure. Yeah, we've not done that. At these frequencies, doing that in our setup, getting a plane wave, we need quite a lot. Yes.
When you're showing the examples from the existing
yes.
Is that actually masking that there are multiple bands there?
So in their model, they just have 1 degree of freedom, so they just have one band. Because their mass spring model is just one displacement component. Here, because we have top and bottom, we can have So this is like a coupled surface wave problem. Actually, there's one on the top and the bottom. So let's just go to the next order. So that's what we're starting to do. Maybe we'll end up at L equals 10 someday. I don't know. So I'm going to do this in an elastic case with Meccano, and I should be careful here. This has to be Meccano-like because we didn't actually buy Meccano. So we started looking at this stuff for looking at surface acoustic wave devices, so small scale elastic waves. And I was playing around with beams and springs, and one of my colleagues sort of jokingly / mockingly said, well, couldn't you just do this with Meccano because it's just a system of beams? And so I then got very excited and found all the old engineering drawings of Meccano and went and modeled it up. And then we went and got our own Meccano made because Meccano nowadays is plastic. And so there's one person in the UK that hoards all of the spare metal Meccano, and it's very, very expensive if you try and buy it. Or you can use Erector. We submitted this got accepted in Physical Review Applied, which is an American journal, and they wanted us to use Erector because that's their sort of version of Meccano, but we stuck to our guns and said, no, we'll stick to Meccano, please. And so this is our system, and so this might answer the question of what's the unit cell. So the system that we have is a beam that's at the center of this that goes all the way along our structure, and then off this we have these arms, and they do our nearest neighbor coupling. So the arms can we only consider the low 2 bending modes, whether in phase or out of phase. And then we add this scaffolding above and below that connects to the 3rd unit cell along. And so you can think, oh, this is my unit cell, and if I make that periodic, then I recover the structure. But actually, you can just chop that guy at the width of 1 unit cell, and so this is exactly the same picture from the acoustic case. So this is our unit cell here. So the periodic boundary conditions, this guy matches to the one over, etc., etc. And so if you tile that 3 times, you then recover this guy here. And then we went exactly as we would do when modeling these things with masses and springs. We turn to a toy model. We're looking at the lowest 2 bending modes, so we have 2 chains of masses. So the junction points where we bolt this thing together, they act like our mass, and the beams themselves, when they bend, that acts like our spring. And so here's very similar finite element simulations that come out of a full model. A normal forwards wave where direction of propagation and energy flow are in the same direction, and then you get this backwards wave effect where your eye is sort of tricked to thinking that the wave is sort of moonwalking. And so we then went and looked at this, and the joy of the toy mass model is that we can then play around with it and to look at what happens when we break these symmetries. So if we were to just do local coupling, each mass is connected to its nearest mass. This non-local or beyond nearest neighbor, we just add some crazy amount of springs that connect this mass to 1 3-unit cells over. So this is starting to represent in a toy model the Meccano system we have. And so second equation of the day is exactly the same as the first. We have some mass spring model. We solve for the displacements in the top and the bottom rails of our masses, and we solve this eigenvalue problem here. Get an undergraduate to do that. But the point of it is that we can then look to see what happens when we break these symmetries. So this is what we would call the symmetric configuration, where we're not breaking anything. All the masses and the springs are all the same. We have 2 modes because we have 2 degrees of freedom. They both have this roton-like structure. That's very nice. Then what happens if we make one of the masses heavier? We break the symmetry, we lift the degeneracies, and we have something that you could argue is more interesting than a roton dispersion. You could remove one of the springs or make them the same, and then again you quite drastically change the dispersion relation here. So the advantage of doing this, obviously in the toy models we can do it very quickly, and then the selling point of our Meccano is that you can take it apart and put it back together again. It's not a trivial task, it takes hours to do because it's very, very fiddly, but that's exactly what we did. So the analogy to the previous is that this is our symmetric case. It's periodic in this direction, so these are our arms that modulate the nearest neighbor interaction. This is the scaffolding that goes above and below. You see we have these 2 bands that behave as we expect. Then this is like when we have more mass, so we put more of this beam on this side, so we displace it along this axis here, we lift the degeneracies. And then on the bottom one, not amazingly obvious, but these 2 have a rotational symmetry because the connectors are cross like this. So when I rotate it round, they still remain cross. In this one, they're now parallel. So when I rotate it, everything is now in the opposite direction. And so the coloring here is similar to what I did before, and it's to reiterate this idea that there's 2 competing channels of power flow. So I integrate the complex mechanical energy flux on 2 regions. In green here on the arms that give our nearest neighbor coupling, and that's what's colored on the right-hand plot. And then on the left-hand plot, I integrate it just on the top and the bottom of the connecting piece, this next nearest neighbor interaction. And you see basically when one is red, the other is blue. And so that means they're in opposition to each other. So there's these 2 avenues that the energy carried by the wave can travel in. And it's the competition between the 2 of them that drives these maxima and minima within the dispersion. And so we had the sample that we manufactured, the assembly, we then followed, described by the reviewer, a gratuitous Blender diagram that took probably far too long to draw. Also, I challenge anyone to try and display wave vector in units of per inch, and they also don't like that. So because we were true to the original mechanical design, so all the spacings of the holes is half an inch. And then as evidence for me being the theorist in the group actually getting my hands dirty, this is my dirty hand. We went and got our Meccano laser cut, and then I spent a morning in engineering bending 200 pieces. You can see it's not particularly good. Like they're not very uniform, but nevertheless, this really did work. And so after several hours of building it, this is the sort of beastly construction that we have. It is a lot more rusty and sorry looking than it is in this picture now because it's been kept near our water tank. And so what we do is then we attach a shaker at different positions of this and we just vibrate the thing. And it's really low frequency, so you can see it. It's really quite nice. Typically, when you would measure something like this, you would use a laser, some LDV type system to get displacement or velocity components. But we had an awful time trying to find one or borrow one. Engineering were really weird and they wouldn't let us borrow theirs either. So what we did was we just measured this acoustically, which I couldn't really believe how well it worked. Tim said, well, why don't we just stick a microphone really near this? This thing doesn't radiate sound, but there's a local pressure fluctuation by this beam. And hopefully this video plays. So we shake it here and you can see these guys wobbling. And so we shake it at a discrete frequency, let it get to steady state, record the sound, then cycle up the next frequency, next frequency, next frequency. And then we move this guy manually over and over and over. We do have a scanning stage, as I showed earlier. This is too big for that, so we had to do everything painstakingly manually. It had to be done upstairs, so everyone had to be very quiet. It took hours and hours and hours to scan, but definitely worth it, I think. This is Tim's very detailed sketch of what's actually going on. We have a sync between our shaker and microphone, and we just record everything. We ensure that the microphone's the same distance away from each of the sort of flanges by using a little spacer. And then we excite in two different positions. One that will excite even modes where the beams bend in phase, and one where there's actually a mix, because we're not exciting perfectly out of phase with two sources. And this is the results we have. So on left-hand side in green, that's from a full finite element simulation that's the same 41 cells, and then I apply a boundary force to that, and I actually take off the displacement field as you would with a laser. And then on right is our acoustic version of that, where we've mapped these local pressure fluctuations. So A and B are for the symmetric configuration. A is when we excite at the bottom, where we get a mix of both the odd and the even modes. And B is when we excite at the center, so we excite something that's predominantly even, and you see, so we've selectively excited one of the modes. And then C or D when we have the asymmetric configuration, and the one where the connectors are parallel. So everything seems to tie together very, very nicely. So we've confirmed that you can have this reconfigurable material, which you can take apart and put back together with some interesting dispersion relations. And so now I want to briefly say why you might want to do any of this in the first place, and relate it to some applications which I spoke about in January. So forgive me if people have seen this. And this is now, we're now stepping away from the Beyond-Nearest-Neighbour, because we haven't actually done this with Beyond-Nearest-Neighbours. That's what we're working on at the moment. But one of the hopes and goals, if you have some vibrating system, is that you can control the vibrations and perhaps siphon some of the energy associated with them through piezoelectric materials. So this might look familiar to some of you. We now have a beam, so this is like the beam that runs through the center of our device, and these rods that come off it are like our nearest neighbor interaction beams, and you slowly change the height of these such that you can adiabatically slow down the wave as it travels through. So we do some physics hand wavy analysis of this, where we assume that when the wave is at a given rod, because the heights don't vary that much, it feels like it's in an infinite periodic medium of that rod height. Daniel and his colleagues have done this properly, so please correct me if I'm wrong with that. But that's how sort of we look at this, and then we make sure that it reaches a zero group velocity mode at a position where we put a harvester. So this was work done by Jacopo De Conti in Milan and Andrea Colombi, who's in Zurich. And so at one of the rod positions, they put a piezoelectric harvester, and the idea of surrounding this by some slowly varying metamaterial means that you can get an amplification of the power from the piezo. There's a time delay before you get to the peak, because we've slowed down the wave as it travels through the system, and therefore the energy that you get out of this is much improved. So Jacopo did these numerically a few years ago, and then they actually went and built the thing and did it experimentally. So these are their experimental results, where they show energy amplification through this idea here. And so just to convince you that it is worth doing, they also simulated a conventional harvester from sort of industrial standards that gets a tiny, tiny amount of energy compared to what they get with their graded surface. So the hope that we will then do now is that we'll take our Beyond-Nearest-Neighbour Metamaterials and grade them as well. And why that's important is because you want to ensure that you have a zero group velocity mode within the first Brillouin zone, and not just due to the drag condition. And that's exactly what these Wotan-like or Beyond-Nearest-Neighbour ones do. And so we did some analysis on this some years ago, where we showed that if you do that and you leverage these zero group velocity modes within the first Brillouin zone, then actually you can get more elastic energy out of the system. So this again isn't Beyond-Nearest-Neighbour. We were looking at beams on rods on a beam, and then the grading now, rather than changing the height, was due to this rotation of the unit cell. So some of this might be familiar, because I showed this earlier. So I'll just let these simulations run. My laptop always freaks out when I run these, so please forgive me if they're a bit jittery. They all have the same impulse. This one looks like it's got more, but we've just not normalized the color bar. But the point in this animation is that if you grade your structure so that you hit one of these maxima or minima within the first Brillouin zone, you'll see that the reflection is much reduced from the front of the device, and the wave stays in your device for a lot longer time, so you can harvest more energy from piezoelectric materials. So that's hopefully where we're going to take these beyond nearest neighbor things, because they, by virtue of their non-local interactions, have potentially many of these maximum and minimum that we can leverage. So you see, after the same amount of time, these rods where we stick our piezoelectric material are still vibrating like crazy, and everything else from these other two arrays where we don't utilize this are basically dead. So I hope that's been of interest and not too physicsy, only a few equations, but just to conclude that this is very much a new and in vogue field, although it comes from some quite old work that Brillouin did almost 70 years ago. I was thinking of how to pitch this in terms of multiple wave scattering, because that's what we're at, and we could perhaps call this selective multiple wave scattering. We have lots of these things, and I'm saying I want to interact with this one very strongly, and that's one thing that these metamaterials can control. And so it allows us to tune their dispersive properties, which we can use for energy harvesting. And one last shameless plug, if you'll allow me, we have a few spaces left on this summer school we're running in August, which is very much hands-on based. So if anyone has any young PhD students or wants to come themselves, please feel free to report that. So thank you very much for your attention. I'll take any questions.
So there's a question.
Sasha, yeah.
First of all, it's a really great talk. I just wanted to mention that in addition to microstructures, you can find simple computer models that show you this kind of use.
Yeah.
So for example, there is a so-called dividing beams.
Mm-hmm.
It's a beam rotation.
Yeah.
Have extra
Yeah.
And of course, they're just beam. So you and of course, actual beam.
Yes. Yeah.
See exactly as you
Yeah. Yep.
So, of course, there's this kind of
Yeah, I think in the elastic systems it's almost natural. So Jacopo, who did the experiments, he has another paper where they don't look at pre-stress, but they look at rods again, and it's the competition between torsion and flexure that gives you this dip, and they also called it Roton-like to jump on the bandwagon, but yeah, so it's yeah.
So you have the expansions nested along the substrate.
Yeah.
The substrate is elastic and it's a chip. It's much acts on the substrate.
Mm-hmm.
So the top
Yeah. Yeah, that's true. Yeah. Yeah, very true actually. So maybe we have done. Yeah, you're right. Yeah. That's great, thanks.
solid state physics. All the time ago, people know that.
Absolutely, yeah. I think we've reinvented the wheel again. Yeah.
Dispersion relation.
Yes, yes.
You know,
It's
before transitional curve.
yes.
There's something like a formula.
Exactly, yeah.
It's signature of instability.
Yeah.
Of crystal structure.
Yeah.
Is about to transition to another structure.
Yes, you're right. Yeah.
So generally, is such kind of so-called Roton-like dispersion relations. They
increasing solid stability is interpreted as some kind of onset of instability. There's no such interpretation for that.
I don't think there may well be, but in the literature that's out on it, which is fairly fresh, that nobody talks about instability.
So that fairly interesting probably.
Yes. Yes, as I said, maybe I'm being a bit flippant when I say, we've reinvented the wheel, but this is very well-established theory, but people in the metamaterials community are getting excited about it because we can, I think probably because of advances in manufacturing techniques, the 3D printing structures that we had, it makes it more possible to do things with it. So that's probably where the excitement's coming from.
Is it possible to write this equation, this Meccano system, or no?
I think it would be, yes, but we didn't bother.
So we should play with the length of the connection, the long range connection.
Yeah.
By you add 50% to this length. What does it change?
It's a good question. I'm not sure. I'd have to think, because the positions of where these turning points are. So if we look at this with this maxima and minima, they're at. So we have L equals 3 here. They're at 1/3 and 2/3 along. So basically, yeah. So I think if you then start changing the parameters, you will change the approach to the turning point. It's like it's inherited a larger periodicity. Exactly. Yeah. So that's exactly what. Maybe
after that's why this length play a role.
I think so. Yeah. So in this slide here, that's essentially what they did here. They increased the coupling strength. So.
Just a friend, but except for if it's possible to go to this quick figure system, it will be something that it will be possible by changing the length.
No, I'm not sure.
I suspect you get a similar effect to this. That's why I asked. It's A through A. If you vary the length inside of it, the wave is experiencing two different lengths to play with. So in the unit cell, it travels 3L or 3L over 2.
Yeah.
While the shift periodic structures is still.
It's still So
this is moving around that.
Yeah.
You want to consider the problem. Every mass or other mass. Infinite.
Yes.
With a decreasing interacting strength with business for them. That's like a discretized dipole model.
Yes.
Okay.
I'm not aware of that in the context of metamaterials,
that
but
would be like discretizing.
Something
the restaurant.
I think it will be a continuous model.
Yeah.
On the other anisotropic applications, where the root velocity and phase velocity are not parallel. What you have at the moment, I think. The ways we're going that way.
Applications. That's always the killer.
Well, I mean,
or
people in it.
Yes. So particularly now when so everything we've done is in 1D, but Wegener's group have now done the 2D extension of it, and they have some really wacky isofrequency contours, and they get all sorts of it's really nice stuff.
You could also break time reversal symmetry.
Absolutely, yeah.
So you've got a length 3L this way, but then as you say, change the length this way.
Yes.
So then there's one spoon diagram like this, and the other one.
Yes. Yeah, of course. Yeah, so I think now that the framework's here and everybody's excited about it again, I would expect all these ideas to come out relatively soon. So watch this space, I guess.
The first one, because you have that gift, it means that you have minimum phase velocity in your system.
Yes.
So it means that if you have something which travels with the lower velocity than that minimum, it starts taking away energy from that from that source. Have you tried? I think you have tried to put it in a flow, like in turbulence flow.
So I haven't, but Tim at Exeter,
Yeah.
he's got a big collaboration with Virginia Tech, and so he was over
So
there a
that's
few
what
months
they
ago.
did, that's
Yeah,
what they did.
exactly. Yeah.
Can you share a little bit?
Honestly, I couldn't comment. I don't know what really they're writing it up at the moment. Yeah, but that's one of the areas that we're taking metamaterials with flow. Yeah.
And then maybe we'll start with the last one.
Sure. Yeah. I'm around after.
It's a very nice one.
Thank you.
So first of all, just a little comment because I got to know that the system is in 2011 and we published the paper that kind of
Cool.
but it's the cost minus.
Yes.
There's an article there like
Yes. I have. Yes. Yeah, I've seen it. Okay.
it's called something like interest
Yeah.
or something like that. And but we was thinking about that specific example before. We have many statements all interactions,
Yeah.
interactions. But we also have the homogeneous model
Uh-huh.
that is classified in what I would like to ask you, do you think that you can construct a kind of homogeneous model for the material composed of crossed tubes, crossed channels?
Yes, I think so. I think somebody has done that. Yes. Yes.
Because then this type of phenomenon can be studied using the macroscopic approach.
Yes. Yeah.
Homogenized approach.
Yeah.
You can see
Yeah, I think in Wegner, so they publish the simulations and the theory, and then they have a science advances paper where they do the experiments, and in the supplementary material to that, I think they do the homogenized model. Yeah, it's really nice.
So let's thank Greg again, and we'll have our
Thank you very much.